The increasing frequency and intensity of extreme weather events pose a significant challenge to electricity networks worldwide. Statistics reveal that approximately 90% of power outages are caused by extreme weather, with 80% occurring on distribution networks. The recent storm Arwen in November 2021 demonstrated this vulnerability, causing over 1 million customers to lose power, with more than 40,000 remaining without electricity for over 3 days. Similarly, Storm Eowyn in January 2023 resulted in over 1 million homes and businesses losing power. These events have prompted significant responses from regulatory bodies like Ofgem and governments, leading to additional measures and funding to tackle the resilience challenge. As part of RIIO-ED3, electricity distribution companies are now required to submit climate resilience strategies that consider not only current weather conditions but also future climate scenarios, recognizing that network resilience is more important than ever. The vulnerability of power systems to extreme weather stems from several critical factors. Overhead distribution feeders are particularly susceptible, with trees and wind causing conductor breaks and pole failures. This is where most service interruptions occur, as distribution lines are less robust than transmission systems and represent the majority of long outages after storms. Cascading faults and slow sectionalizing present another vulnerability, as radial distribution designs mean a single fault can affect many customers, while the lack of automated sectionalizing allows transient faults to become sustained outages. Critical transmission choke points, such as towers and lines vulnerable to extreme ice and wind, experience slow and costly restoration when damaged. Operational and human factors, including inadequate situational awareness, workforce constraints, and poor prepositioning and communications, multiply outage duration, as highlighted in the Storm Arwen review. Finally, interdependencies and cascading social impacts create additional complexity, as telecommunications, transport, and water systems interact, with loss of power potentially degrading restoration capability and welfare outcomes. Several proven technical measures can significantly improve power system resilience to extreme weather events. Distribution automation and self-healing schemes represent one of the most effective approaches. Automated sectionalizing through reclusers and automated switches, combined with fault location/isolation/restoration, FLISR, systems and advanced distribution management systems, ADMS/OMS, reduce outage size and duration by isolating faults and re-energizing healthy sections within seconds to minutes. Economic assessments consistently show clear benefits for many feeders implementing these technologies. These self-healing systems can reroute and restore power automatically when a problem occurs, preventing temporary faults from becoming sustained outages and improving overall reliability and resilience. Targeted hardening of physical infrastructure provides another proven approach to resilience enhancement. This includes replacing vulnerable wooden poles with composite or steel alternatives, reinforcing pylons, fitting stronger crossarms and guying, and selective undergrounding for critical feeders or the most exposed corridors. While these measures are expensive, prioritization by exposure and criticality ensures resources are directed where they deliver the most benefit. Following Storm Arwen, additional funding was provided to distribution network operators through a price control reopener mechanism specifically for such measures, demonstrating their recognized importance. Vegetation management at scale represents another critical proven measure. Frequent, risk-based tree trimming enhanced by GIS and remote sensing technologies significantly reduces contact faults between trees and power lines. Combining LiDAR scanning with outage history models allows utilities to focus resources where they deliver the most benefit, optimizing maintenance efforts and preventing many outages before they occur. This proactive approach is particularly valuable given that vegetation-related incidents account for a substantial portion of weather-related outages. Distributed energy resources, DERs, and storage systems offer additional resilience capabilities. Battery energy storage systems, BESS, combined with local generation and controlled islanding enable critical loads to be served when feeders fail. Microgrids for hospitals, emergency centers, and tight communities materially reduce welfare impacts during outages by maintaining power to essential services. These distributed resources provide both resilience and flexibility benefits, creating more robust local energy systems that can operate independently from the main grid when necessary. Transmission resilience measures include tower design upgrades, accelerated inspections using drone technology, selective line replacement, and building redundancy through parallel paths and HVDC links where economically justified. These measures enhance the backbone of the power system, ensuring that bulk power transfer capabilities remain intact during extreme weather events. Workforce and logistics improvements, including pre-positioning crews, cross-utility mutual aid agreements, and better welfare support planning, are also essential operational measures that the Storm Arwen review found were insufficient and that regulators now require to be addressed. Advanced and emerging technologies are increasingly shaping the future of power system resilience. Grid-forming inverters and DER orchestration represent a significant technological advancement. Unlike traditional inverters that simply follow grid conditions, grid-forming inverters can establish voltage and frequency references, enabling resilient islanding and stable microgrids that make high renewable systems more resilient to disturbances. This technology is an active area of research and deployment, with promising results for enhancing system resilience while supporting renewable energy integration. Artificial intelligence and predictive maintenance, combined with digital twin technology, offer powerful capabilities for resilience enhancement. Machine learning models using weather data, asset condition information, and historical outage patterns can predict failure risk and optimize maintenance and vegetation crew deployment. Digital twins allow utilities to test scenarios for extreme events and optimize investment planning, creating virtual replicas of physical assets that can be used for simulation and analysis without risking actual infrastructure. These technologies enable a shift from reactive to proactive maintenance strategies, addressing potential issues before they lead to outages. Wide area sensing and fast controls provide another technological frontier for resilience enhancement. Phaser measurement units, PMUs, enhanced telemetry, and low-latency communications help prevent cascading failures at transmission scale and speed up restoration. These technologies provide real-time visibility into grid conditions, allowing operators to detect and respond to issues more quickly and effectively. High-voltage direct current, HVDC, and meshed transmission systems offer additional resilience benefits, providing controllable, weather-resilient bulk transfer that is less susceptible to AC stability issues during disturbances. These longer-term backbone investments improve system flexibility and create more robust transmission networks. Materials science and asset innovation also contribute to resilience improvements. Composite poles, anti-icing conductors, improved insulators, and corrosion-resistant fittings extend asset life and reduce weather vulnerability. These material advancements create more durable infrastructure that can better withstand extreme weather conditions, reducing the likelihood of failures and extending maintenance intervals. A practical, prioritized roadmap for enhancing power system resilience requires coordinated action across multiple time frames. In the short term, 0 to 3 years, high-impact, relatively low-cost measures should be prioritized. These include deploying ADMS/OMS upgrades and automated reclusers on the most outage-prone feeders to implement self-healing capabilities, strengthening vegetation management using remote sensing technologies, and improving outage communications and crew logistics through pre-positioning protocols and mutual aid contracts. These measures can be implemented relatively quickly and deliver immediate resilience benefits. Medium-term priorities, 3 to 8 years, focus on targeted capital works and DER deployment. These include selective pole replacement and undergrounding for high-risk corridors, prioritizing critical infrastructure feeders, scaling community microgrids and BESS at critical sites such as hospitals and shelters, and starting pilots for grid-forming inverter controls and integrated DER orchestration. These investments require more planning and capital but deliver substantial resilience benefits. Long-term priorities, 8 to 20 years, involve systemic change requiring new financing and regulatory approaches. These include transmission backbone upgrades, increased meshing, and HVDC corridors where needed, full adoption of digital twins, pervasive sensors, and AI-driven asset management, and regulatory frameworks that fund resilience investments at scale, such as RIIO-style multi-period plans with resilience KPIs. These long-term investments create a fundamentally more resilient power system but require significant coordination and resources. Investment prioritization should follow a structured decision framework based on hazard mapping, cost-benefit analysis, and flexibility assessment. The framework should identify where weather hazard exposure intersects with high vulnerability and high societal/economic consequence, quantify the value of loads served during outages to justify hardening and DER investments, calculate the marginal benefit of automation, outage minutes avoided per pound invested, and assess the flexibility value of DERs and storage that deliver both resilience and capacity benefits. This approach ensures that limited resources are directed to investments that deliver the greatest resilience benefits. Regulatory and planning changes are essential to support these investments. Risk-based planning and climate-forward standards require utilities to use future climate scenarios for planning rather than historical reliability metrics. Targeted incentives and funds, such as Ofgem's Strategic Innovation Fund, enable rapid deployment of resilience technologies. Cost recovery frameworks for resilience investments must balance consumer affordability with long-term avoided costs from outages. Standardized resilience metrics and reporting, including resilient SAIDI/SCI-FI adjusted for extreme events, scenario-based resilience indices, and public climate resilience strategies, provide transparency and accountability. With innovation, investment, and collaboration across utilities, regulators, governments, technology providers, and partners, we can transform power systems to build an outage-free, sustainable electrical energy future. The history of electricity networks is one of innovation and technological progress, from Edison's Pearl Street Station to the complex system we know today. As we focus on resilience in the face of increasing extreme weather challenges, this tradition of innovation must continue, with all stakeholders working together to implement the proven and emerging technologies that will create a more resilient power system for the future.